In the stillness that surrounds us, beneath the glow of screens and the hum of daily routine, there exists a light that has traveled farther than comprehension easily allows. Before we continue, consider watching this in full screen, and if you find value in what unfolds here, subscribe so we can explore these depths together. What follows is not a story of triumph or discovery framed in simplicity, but rather an examination of something the James Webb Space Telescope has detected, light that, according to our most reliable models of cosmic history, should not exist at all. The light in question does not arrive from a nearby star or a familiar galaxy charted in previous surveys. It comes from a region of space-time so distant that the universe, at the moment this light was emitted, was not yet old enough to have assembled the structures we now observe. The light carries with it information encoded in wavelength, intensity, and spectral signature, information that, when measured and interpreted, suggests the presence of fully formed galaxies, stars already aged, and chemical compositions that require generations of stellar life cycles to produce. Yet the cosmic clock, as calculated from the expansion of space itself, from the cooling of the cosmic microwave background, from the decay rates of primordial elements, tells us that insufficient time had passed for such objects to exist. This is not a matter of instrumentation error, nor is it a fleeting anomaly dismissed after peer review. The James Webb Space Telescope, positioned beyond the interference of Earth's atmosphere, equipped with infrared sensors calibrated to detect the faintest and most ancient emissions, has returned data repeatedly across multiple observation campaigns, showing galaxies that appear too bright, too massive, too chemically mature for the epoch in which they are observed. The redshift values, which serve as our primary measure of cosmic distance and time, place these objects in an era when the universe was only a few 100 million years old, a sliver of time compared to its current age of 13.8 billion years. To understand why this constitutes a profound challenge, one must first grasp what it means for light to travel across cosmological distances. Light does not move instantaneously. It propagates at a fixed speed, roughly 300,000 kilometers per second in a vacuum. And this speed, while extraordinary by terrestrial standards, is finite. When we observe a distant object, we are not seeing it as it is now, but as it was when the light we detect began its journey. The farther away an object lies, the longer its light has been traveling, and the further back in time we are looking. This principle transforms every telescope into a time machine, allowing us to observe not the present state of the universe, but its past. The James Webb Space Telescope was designed explicitly to exploit this effect. Its infrared capabilities allow it to detect light that has been stretched by the expansion of space itself, light that was emitted in the visible or ultraviolet spectrum but has been redshifted into the infrared by the time it reaches us. This redshift is not merely a color change. It is a direct consequence of the universe's expansion, encoded in the wavelength of every photon. By measuring the degree of redshift, astronomers can determine how much the universe has expanded since the light was emitted, and from that, calculate both the distance to the object and the cosmic time at which the emission occurred. When Webb turned its instruments toward regions of sky previously observed by the Hubble Space Telescope, regions thought to contain some of the earliest galaxies, the expectation was clear. Early galaxies should be small, irregular, dim, and composed primarily of hydrogen and helium, the only elements produced in significant quantities during the Big Bang. Stars within these galaxies should be young, first-generation objects, massive and short-lived, burning through their nuclear fuel in mere millions of years. The light from such galaxies should reflect this youth. Blue or ultraviolet when emitted, redshifted into the near-infrared by the time it reaches us, but still faint, still fragile, still bearing the signature of a cosmos in its infancy. What Webb detected defied these expectations in multiple, overlapping ways. The galaxies observed at high redshift were not dim. They were luminous, emitting light at intensities that suggested stellar populations numbering in the billions, far more than early models predicted could form in such a short time. Their spectra revealed not just hydrogen and helium, but heavier elements, carbon, oxygen, nitrogen, silicon, iron, elements that can only be synthesized in the cores of stars and distributed through supernova explosions. The presence of these elements indicated that multiple generations of stars had already lived and died, that the interstellar medium had been enriched, that the chemical evolution of these galaxies had progressed to a stage typically associated with much older systems. Moreover, the galaxies exhibited structural complexity. They were not mere clumps of gas collapsing under gravity, but organized systems with evidence of rotation, spiral arms in some cases, and central concentrations of mass consistent with the presence of supermassive black holes. The formation of such black holes, objects with millions or even billions of times the mass of the Sun, is itself a process that requires time. Current models suggest that supermassive black holes grow through the accretion of matter and the merging of smaller black holes, processes that unfold over hundreds of millions of years, not the mere few 100 million years available in the early universe. The tension arises because time, in cosmology, is not a flexible parameter. The age of the universe is constrained by multiple independent lines of evidence. The cosmic microwave background, the afterglow of the Big Bang, provides a snapshot of the universe when it was only 380,000 years old. The temperature fluctuations within this radiation, measured with exquisite precision by missions such as Planck, allow cosmologists to determine the expansion rate, the density of matter and energy, and the overall geometry of space-time. These measurements converge on a consistent timeline, one in which the universe expands, cools, and structures form at a pace dictated by gravity, radiation pressure, and the interplay of dark matter and ordinary matter. Within this timeline, the first stars are expected to ignite roughly 100 to 200 million years after the Big Bang, as clouds of primordial gas collapse under their own gravity, fragmenting into denser cores where nuclear fusion can begin. These first stars, known as population 3 stars, would have been massive, metal-free, and incredibly hot, living for only a few million years before exploding as supernovae, seeding the surrounding space with the first heavy elements. The debris from these explosions would then mix with remaining gas, allowing a second generation of stars to form, stars with slightly higher metallicity, slightly longer lifespans, and the beginnings of planetary systems. This process, while rapid on cosmic scales, still requires time. Each generation of stars must form, live, and die before the next can inherit the enriched material. The buildup of heavy elements is incremental, and the assembly of galaxies, through the merger of smaller protogalaxies, is similarly gradual. Dark matter, which comprises the majority of the matter in the universe, provides the gravitational scaffolding upon which galaxies form. But even dark matter halos take time to collapse and merge, following the predictions of hierarchical structure formation. Yet the galaxies observed by Webb appear to have bypassed much of this timeline. Their brightness suggests stellar populations too large to have formed in the available time. Their metallicity suggests chemical enrichment too advanced for their age. Their structural complexity suggests gravitational interactions and mergers that should not yet have occurred. Each of these observations, taken individually, might be reconciled with existing models through adjustments to star formation efficiency, or by invoking more rapid accretion on black holes, or by allowing for more efficient metal production in early supernovae. But taken together, the observations form a pattern that resists easy resolution. One possible explanation is that the early universe was more efficient at forming stars than current models allow. Standard models assume a certain rate of star formation based on the density of gas, the cooling mechanisms available, and the feedback processes that regulate further collapse. Feedback, in this context, refers to the energy and momentum injected into the interstellar medium by supernovae, stellar winds, and radiation pressure from young stars. This feedback heats the surrounding gas, expelling it from the galaxy or preventing it from collapsing further, thereby limiting the rate at which new stars can form. If, however, feedback was less effective in the early universe, or if gas could cool and collapse more rapidly, then star formation rates could have been significantly higher. This would allow galaxies to accumulate stellar mass more quickly, potentially explaining the observed brightness. But this adjustment introduces its own problems. Higher star formation rates would produce more supernovae, which would increase feedback, which should suppress further star formation. The system is self-regulating, and pushing star formation efficiency to high risks, creating conditions that contradict other observations, such as the smoothness of the cosmic microwave background or the abundance of light elements produced in Big Bang nucleosynthesis. Another possibility involves the initial mass function, the distribution of stellar masses that form from a collapsing gas cloud. In the present-day universe, most stars are low-mass, long-lived objects, with only a small fraction being massive, short-lived stars. If the initial mass function in the early universe was skewed toward more massive stars, then each star would be more luminous, and a smaller total number of stars would be needed to produce the observed brightness. Massive stars also produce heavy elements more efficiently and die more quickly, accelerating chemical enrichment. But this too has limits. Massive stars are inefficient at converting gas into stellar mass, and they inject enormous amounts of energy into their surroundings, again enhancing feedback. A top-heavy initial mass function would also alter the appearance of the galaxy's spectrum in ways that should be detectable, and current spectroscopic observations do not consistently show the expected signatures. Moreover, even with more massive stars, the absolute number of stars that can form is still limited by the amount of gas available and the time required for that gas to collapse, fragment, and ignite. The presence of heavy elements, meanwhile, cannot be easily dismissed. Carbon, oxygen, and heavier elements are not produced in significant quantities during the Big Bang. They are synthesized in stellar cores through nuclear fusion, and they are dispersed into the interstellar medium when stars die. The detection of these elements in high redshift galaxies means that at least one, and likely several, generations of stars must have already completed their life cycles. Even if the first generation of stars formed extremely rapidly, they still needed time to burn through their nuclear fuel, explode, and enrich the surrounding medium. For subsequent generations to form, this enriched gas must then cool, collapse, and fragment again, a process that, even under optimized conditions, takes tens of millions of years per cycle. The structural complexity observed in some of these early galaxies adds another layer of difficulty. Galaxies do not form in isolation. They grow through the accretion of gas and the merger of smaller systems, a process driven by the gravitational influence of dark matter halos. In the standard model, small dark matter halos collapse first, followed by the merger of these halos into progressively larger structures. This hierarchical assembly is well supported by simulations and observations of galaxy formation at later cosmic times, but it is inherently a time-dependent process. Mergers require time for gravitational interactions to play out, for orbital energy to be dissipated through dynamical friction, for gas to be funneled into the central regions, where it can fuel star formation or feed a central black hole. If the galaxies observed by Webb already exhibit the structural features typically associated with mature systems, then either the merger process proceeded much more rapidly than models predict, or these galaxies formed through a different mechanism entirely. Rapid mergers would require either a much higher density of proto-galaxies in the early universe, or a more efficient mechanism for dissipating orbital energy. Both scenarios strain existing models without clear physical justification. The supermassive black holes detected in some of these early galaxies present perhaps the most acute problem. A black hole with a mass of 1 billion solar masses, observed when the universe is only a few hundred million years old, must have grown from a much smaller seed. Black holes grow by accreting matter from their surroundings, a process governed by the Eddington limit, the maximum rate at which a black hole can accrete matter before the radiation pressure from infalling material halts further accretion. Even if a black hole accretes at the Eddington limit continuously, starting from a seed mass of, say, 100 solar masses formed from the collapse of a first-generation star, it would take several hundred million years to reach 1 billion solar masses. But the universe at the time these black holes are observed is only a few 100 million years old in total. This leaves almost no time for the seed black hole to form, let alone grow to supermassive scales. To reconcile the observations, theorists have proposed various mechanisms for forming more massive seed black holes, bypassing the need for gradual growth. These mechanisms include the direct collapse of massive gas clouds into black holes of 10,000 to 100,000 solar masses, or the formation of dense stellar clusters that undergo runaway collisions, producing intermediate mass black holes that then serve as seeds. Each of these mechanisms requires specific conditions that may not have been widespread in the early universe. Direct collapse requires gas that remains pristine, unmixed with heavy elements, and that can cool efficiently without fragmenting into individual stars. This is difficult to achieve once the first generation of stars has already begun enriching the interstellar medium. Dense stellar clusters require exceptionally high star formation rates in compact regions, and the collisions must occur before the cluster disperses. Even if these mechanisms operated in rare, special environments, it is unclear whether they could have produced enough supermassive black holes to account for the observed population in early galaxies. The detection of these galaxies and their properties is not a matter of speculation or indirect inference. The James Webb Space Telescope provides spectroscopic data, breaking the light from these objects into its component wavelengths, revealing emission and absorption lines that correspond to specific atomic transitions. These lines serve as fingerprints, identifying the elements present, their ionization states, and the physical conditions within the galaxy, such as temperature, density, and the intensity of the radiation field. The redshift of these lines is measured with precision, allowing astronomers to determine the exact cosmic time at which the light was emitted. The reliability of these measurements rests on the consistency of physical laws across space and time. The wavelengths of atomic transitions are determined by the energy levels of electrons and atoms, which in turn are governed by fundamental constants, such as the charge of the electron, the mass of the proton, and Planck's constant. If these constants were significantly different in the early universe, the spectral lines would appear at different wavelengths, and our interpretation of redshift and cosmic time would be incorrect. However, observations of the cosmic microwave background, of distant quasars, and of the ratios of light elements produced in Big Bang nucleosynthesis all indicate that fundamental constants have remained stable over cosmic history. This stability extends to the expansion of the universe itself. The redshift distance relation, first observed by Edwin Hubble in the 1920s, has been tested and refined over nearly a century of astronomical observations. It is embedded in the framework of general relativity, which describes how space-time responds to the presence of matter and energy. The expansion rate, quantified by the Hubble constant, is not arbitrary, but is determined by the total density of matter, dark energy, and radiation in the universe. These densities are measured independently through multiple methods, including the dynamics of galaxy clusters, the distribution of large-scale structure, and the temperature fluctuations in the cosmic microwave background. All of these measurements point to a universe that is approximately 13.8 billion years old, expanding at a rate that has varied over time due to the changing contributions of radiation, matter, and dark energy. In the early universe, radiation dominated, causing the expansion to decelerate. Later, as the universe cooled and matter became more influential, the expansion continued to decelerate, but at a slower rate. More recently, dark energy has begun to dominate, causing the expansion to accelerate. This history is well established and forms the backbone of the standard cosmological model, known as lambda CDM, where lambda represents dark energy and CDM stand for cold dark matter. The galaxies observed by Webb at high redshift are placed within this timeline based on their measured redshifts. A redshift of, say, 10 corresponds to a time when the universe was roughly 500 million years old, less than 4% of its current age. A redshift of 15 pushes this back to around 300 million years, a time when the first stars were only just beginning to form. Yet galaxies observed at these redshifts appear not as nascent systems struggling to ignite their first stars, but as thriving, mature structures with properties that, in the local universe, are associated with galaxies billions of years old. This discrepancy is not easily dismissed. It is not a matter of a single unusual object that might be explained by rare circumstances or observational artifacts. Multiple galaxies observed in different regions of the sky, across different observation programs, exhibit similar anomalies. Their number densities, the frequency with which such galaxies appear per unit volume of space, are higher than models predict, suggesting that whatever mechanism produced them was not rare, but relatively common in the early universe. One might ask whether the redshift interpretation itself could be flawed, whether these galaxies are not as distant or as ancient as their redshifts suggest. This is an understandable question, but it lacks a viable alternative explanation. Redshift is caused by the expansion of space-time, and the relationship between redshift and distance is not simply a correlation, but a direct consequence of general relativity applied to a homogeneous, expanding universe. To place these galaxies at lower redshifts, closer in time and space, would require either abandoning general relativity or invoking mechanisms that produce redshift through some other means. Gravitational redshift, the shift in wavelength caused by light climbing out of a gravitational potential well, is one such mechanism, but it is far too weak to account for the observed redshifts unless the galaxies reside in extraordinarily deep potential wells, which would require concentrations of mass inconsistent with their observed sizes and luminosities. Doppler redshift, caused by the motion of an object through space, is another possibility, but it would require these galaxies to be moving away from us at velocities close to the speed of light, and there is no physical mechanism that would cause such motions in a large population of galaxies without also producing other observable effects, such as distortions in the cosmic microwave background or anomalies in large-scale structure. Thus, the cosmological interpretation of redshift remains the only viable explanation, and the galaxies observed by Webb are indeed located at the vast distances and early times indicated by their spectral measurements. This leaves the problem squarely within the realm of astrophysics and cosmology. How did these galaxies form so quickly, and what does their existence tell us about the processes that govern the early universe? One avenue of investigation involves refining our understanding of dark matter. Dark matter does not emit, absorb, or reflect light, and its presence is inferred only through its gravitational effects on visible matter, on the motion of galaxies, on the bending of light through gravitational lensing, and on the distribution of large-scale structure. In the Standard Model, dark matter is cold, meaning its particles move slowly compared to the speed of light, allowing structures to form hierarchically from small to large scales. If dark matter were warm, with particles moving more quickly, small-scale structures would be erased, delaying galaxy formation. If dark matter were hot, structures would form top-down, with large systems collapsing first and fragmenting later. Current observations favor cold dark matter, but the precise properties of dark matter particles remain unknown. If dark matter interacts with itself through forces other than gravity, even weakly, it could alter the formation of halos in the early universe. Self-interacting dark matter, for example, could allow halos to collapse more rapidly or to achieve higher central densities, potentially accelerating the formation of the first galaxies. However, such interactions would also affect the structure of galaxies at later times, and observations of present-day galaxies place tight constraints on the degree of self-interaction. Another possibility involves the role of baryonic physics, the behavior of ordinary matter composed of protons, neutrons, and electrons. In simulations of galaxy formation, baryonic physics is notoriously difficult to model accurately. Gas cools through radiative processes, collapses under gravity, fragments into stars, and is then heated and expelled by feedback from supernovae and active galactic nuclei. Each of these processes involves complex physics, from atomic and molecular transitions to magnetic fields and turbulence, and the interplay between them determines the efficiency of star formation and the growth of galaxies. If certain cooling processes were more efficient in the early universe, gas could collapse more rapidly, forming stars sooner. Molecular hydrogen, the primary coolant in metal-free gas, forms through a slow sequence of chemical reactions, and its abundance is sensitive to the radiation background and the presence of trace amounts of heavy elements. If conditions in the early universe enhance the formation of molecular hydrogen, or if other cooling mechanisms, such as fine-structure line emission from carbon or oxygen, became effective earlier than expected, then gas could cool and collapse on shorter timescales. But again, these adjustments have limits. Cooling is counteracted by heating from the radiation produced by stars and accreting black holes. The balance between cooling and heating regulates the rate at which gas can collapse, and pushing cooling efficiency too high without correspondingly increasing heating mechanisms risks creating conditions inconsistent with other observations. For example, excessively efficient cooling would lead to the formation of stars at earlier times, which would produce a higher background of ultraviolet radiation, which would reionize the universe earlier than observed. Reionization, the process by which the neutral hydrogen that filled the universe after recombination was ionized by the radiation from the first stars and galaxies, is itself a key constraint on early galaxy formation. Observations of the cosmic microwave background, particularly the optical depth due to scattering by free electrons, indicate that reionization occurred gradually, with most of the universe becoming reionized between redshifts of 6 and 10. If galaxies formed too early or too efficiently, reionization would have occurred sooner, increasing the optical depth beyond what is observed. The timing of reionization is also constrained by observations of distant quasars. Light from these quasars passes through the intervening intergalactic medium, and absorption features in their spectra reveal the ionization state of the gas. Complete absorption of light at wavelengths corresponding to the ionization of neutral hydrogen, known as the Gunn-Peterson trough, indicates that the intergalactic medium is largely neutral at redshifts above 6 and partially ionized at lower redshifts. These observations are consistent with reionization being driven by the cumulative radiation from early galaxies, but they also constrain the number and luminosity of those galaxies. The galaxies detected by Webb, if they represent a typical population of early galaxies rather than rare outliers, would contribute significantly to the reionization process. Their high luminosities would produce copious amounts of ultraviolet radiation capable of ionizing hydrogen. If such galaxies were common, reionization would have proceeded more rapidly and been completed earlier, potentially in tension with the observed timing. This raises the question of whether these bright, massive galaxies were indeed common, or whether they represent the extreme tail of the distribution, with most early galaxies being fainter and less massive, but not yet detected by Webb due to instrumental sensitivity limits. Distinguishing between these scenarios requires deeper observations, imaging and spectroscopy of fainter objects at high redshift, and statistical analyses of the galaxy luminosity function, which describes the number of galaxies per unit volume as a function of their brightness. If the luminosity function at high redshift is similar to that at later times, with a smooth distribution from faint to bright, then the detection of a few bright galaxies does not necessarily imply an overabundance, merely that Webb is selectively detecting the most luminous examples. But if the luminosity function is skewed with an excess of bright galaxies relative to expectations, then the problem of early galaxy formation becomes more acute. Measurements of the galaxy luminosity function at high redshift are ongoing, and early results suggest that there may indeed be an overabundance of bright galaxies compared to predictions from standard models. This overabundance is quantified by comparing the observed number density of galaxies at a given brightness to the number density predicted by simulations that incorporate dark matter halo formation, gas cooling, star formation, and feedback. The discrepancy is not overwhelming, but it is statistically significant, persisting across multiple independent studies and observation programs. This suggests that the issue is not merely one of rare, extreme objects, but rather a systematic offset between predictions and observations at the bright end of the luminosity function. Such an offset could indicate that star formation was more efficient than assumed, that the initial mass function favored more luminous stars, that feedback was less effective at regulating galaxy growth, or that the hierarchical assembly of dark matter halos proceeded more rapidly than simulations indicate. Each of these possibilities requires adjustments to the physics included in models, and each adjustment must be tested against other observations to ensure consistency. Simulations of galaxy formation operate by tracking the evolution of dark matter and baryonic matter from the early universe to the present day. They begin with initial conditions set by the fluctuations observed in the cosmic microwave background, small overdensities and underdensities in the distribution of matter. These fluctuations, imprinted during the inflationary epoch in the first fraction of a second after the Big Bang, grow over time under the influence of gravity, with overdense regions pulling in more matter and becoming denser, while underdense regions lose matter and become voids. Dark matter, being collisionless and non-radiative, collapses into halos, structures bound by their own gravity. Baryonic matter, which interacts through electromagnetic forces, initially follows the dark matter, but then undergoes more complex behavior. Gas falls into dark matter halos, is shock-heated to high temperatures, cools through radiative processes, and settles into rotating disks or irregular distributions, depending on the halo's mass and angular momentum. Once the gas is sufficiently dense and cool, it fragments into molecular clouds, and within these clouds, stars begin to form. The feedback from these stars, through radiation, stellar winds, and supernova explosions, injects energy and momentum back into the gas, heating it, expelling it from the galaxy, or suppressing further collapse. The balance between infall, cooling, star formation, and feedback determines the final properties of the galaxy, its mass, size, star formation rate, and chemical composition. Simulations attempt to capture all of these processes, but they rely on subgrid models, simplified prescriptions for processes that occur on scales smaller than the simulation can resolve, such as the formation of individual stars or the propagation of supernova shocks through a turbulent medium. These subgrid models contain free parameters, values that are adjusted to reproduce observed properties of galaxies at later times, such as the galaxy's stellar mass function or the relationship between galaxy mass and star formation rate. Once calibrated, the models are used to make predictions about earlier times when observational data were scarce. The detection of unexpected galaxies by Webb suggests that these extrapolations may not be reliable, that the physics of galaxy formation at early times differs in important ways from that at later times. One factor that may differ is the nature of the first stars. Population 3 stars, as they are known, form from gas composed almost entirely of hydrogen and helium, without the presence of heavy elements that, in later generations, facilitate cooling and allow gas to fragment into smaller, lower-mass stars. Without these coolants, the gas in primordial clouds can only cool through molecular hydrogen, and the minimum mass for a collapsing cloud to fragment and form a star is much higher, resulting in stars that are tens or even hundreds of times more massive than the Sun. These massive stars are extraordinarily luminous, emitting vast amounts of ultraviolet radiation, and they live for only a few million years before exploding as supernovae or collapsing into black holes. Their supernovae are energetic, dispersing the heavy elements they produce across large volumes of space, and the radiation they emit ionizes the surrounding gas, creating bubbles of ionized hydrogen that expand into the neutral intergalactic medium. The collective effect of many such stars would have been to gradually reionize the universe, but the process is not instantaneous, and the patchiness of reionization, with some regions ionized earlier than others, affects subsequent star formation. In regions that are ionized early, the gas is heated to tens of thousands of degrees, increasing its pressure and making it more difficult for gravity to compress it into new stars. This negative feedback could suppress star formation in small halos, preventing them from forming galaxies, and funneling star formation into larger halos where gravity is strong enough to overcome the increased pressure. If this process was more pronounced in the early universe than models account for, it could lead to a scarcity of low-mass galaxies and an overabundance of high-mass galaxies, consistent with the observations of bright galaxies by Webb. Conversely, in regions that remain neutral longer, gas can cool and collapse more easily, potentially leading to bursts of star formation that produce the observed brightness. But this would also imply a more extended and uneven reionization process, with significant spatial variation in the ionization state of the intergalactic medium, which should be detectable in observations of the cosmic microwave background or in the spectra of distant quasars. Current data do indicate some patchiness in reionization, but the degree of variation is constrained, and it is not yet clear whether it can fully account for the observed properties of early galaxies. Another consideration is the efficiency with which gas is converted into stars. The star formation efficiency, defined as the fraction of gas in a galaxy that is converted into stars per unit time, is a key parameter in models of galaxy formation. It is typically assumed to be low, a few percent per orbital time, based on observations of star-forming regions in the present-day universe. This low efficiency reflects the fact that much of the gas in a galaxy is not dense enough to form stars, and that feedback processes disrupt molecular clouds before all of their gas is consumed. If star formation efficiency was higher in the early universe, perhaps because molecular clouds were more tightly bound, or because feedback was less effective at dispersing them, then galaxies could accumulate stellar mass more quickly. However, increasing star formation efficiency also increases the rate at which gas is consumed, potentially exhausting the gas supply before the galaxy has had time to grow as large as observed. This creates a tension. Higher efficiency produces more stars more quickly, but also limits the total stellar mass that can be achieved unless the gas supply is continuously replenished through accretion from the intergalactic medium. The accretion of gas onto galaxies is itself a complex process. Gas can be accreted smoothly, flowing along filaments of the cosmic web, or it can be accreted in clumps through the merger of smaller protogalaxies. Smooth accretion is thought to dominate at early times, feeding gas into galaxies at a rate determined by the density of the surrounding medium and the depth of the gravitational potential well. Clumpy accretion, through mergers, becomes more important later as the number density of galaxies increases and gravitational interactions become more frequent. If gas accretion rates in the early universe were higher than models predict, perhaps because the cosmic web was denser or because feedback was less effective at expelling gas from halos, then galaxies could sustain high star formation rates for longer periods, building up the observed stellar masses. But higher accretion rates would also increase the rate at which gas is shock heated as it falls into the halo, potentially raising the gas temperature and making cooling more difficult, which would counteract the benefit of increased accretion. These interlocking dependencies illustrate the challenge of modeling galaxy formation. Every process affects every other process, and adjusting one parameter to better match observations often degrades the match in another area. This is why simulations are run over a range of parameter values, exploring the multidimensional space of possibilities, and why the consistency of a model is judged not by its ability to reproduce a single observation, but by its ability to simultaneously match multiple independent observables. The galaxies detected by Webb provide new constraints on this parameter space, constraints that were not available when many of the current models were developed. Incorporating these constraints will require not only adjusting parameters within existing models, but also considering whether new physics needs to be included, physics that is currently neglected or treated in simplified ways. One area that may require more careful treatment is the role of magnetic fields. Magnetic fields are present in galaxies, in the interstellar medium, and even in the intergalactic medium, though their strength and structure vary widely. Magnetic fields affect the dynamics of gas by providing additional pressure support, by channeling gas flows along field lines, and by influencing the propagation of cosmic rays, high-energy particles that can heat the gas and provide an additional source of pressure. In simulations, Magnetic fields are often neglected or treated in a simplified manner because they are computationally expensive to model accurately. But their effects on star formation and feedback could be important, especially in the early universe where conditions were different from those today. Another area that may require refinement is the treatment of turbulence. Gas in galaxies is not smooth and quiescent, but is stirred by the energy input from supernovae, stellar winds, and gravitational instabilities. This turbulence affects the rate at which gas can collapse into stars, creating a hierarchy of eddies and fluctuations that compress gas in some regions while rarefying it in others. The interaction between turbulence, magnetic fields, and gravity is highly nonlinear, and capturing it accurately in simulations requires very high resolution and sophisticated numerical methods. Similarly, the formation and growth of supermassive black holes in the early universe may involve physics that is not fully captured in current models. Black holes grow by accreting gas from their surroundings, but the rate of accretion is limited by the need for gas to lose angular momentum and spiral inward. This can occur through gravitational torques exerted by non-axisymmetric structures, such as bars or spiral arms, through viscous dissipation in an accretion disk, or through interactions with binary companions or stellar clusters. Each of these mechanisms operates on different timescales and under different conditions, and the dominant mechanism may have varied over cosmic time. In the early universe, gas was colder and denser on average, which could have facilitated more rapid inflow onto black holes. The lack of heavy elements meant less radiative cooling from metal lines, but molecular hydrogen cooling was still effective in sufficiently dense regions. The balance between cooling, heating, and angular momentum transport determined how efficiently gas could be funneled to the center of a galaxy and onto the central black hole. If this balance favored more rapid accretion than current models assume, it could explain the presence of supermassive black holes at early times without requiring exotic seed formation mechanisms. However, rapid accretion also produces strong feedback. As gas spirals onto a black hole, it is heated by friction and compressed, emitting intense radiation across the electromagnetic spectrum. This radiation, particularly in the ultraviolet and X-ray bands, can ionize and heat the surrounding gas, driving powerful winds that expel material from the galaxy and suppress further accretion. This feedback, known as active galactic nucleus or AGN feedback, is thought to play a key role in regulating the growth of both the black hole and the host galaxy, establishing the observed correlations between black hole mass and galaxy properties. If AGN feedback was less effective in the early universe, perhaps because the gas was denser and more tightly bound, or because the geometry of the accretion flow was different, then black holes could have grown more rapidly without self-regulating their growth. But less effective feedback would also mean that more gas remained in the galaxy, leading to higher star formation rates, which should make the galaxies even brighter than observed, potentially overshooting the observations in a different way. The interplay between star formation, black hole growth, and feedback is further complicated by the fact that these processes do not occur uniformly throughout a galaxy, but are concentrated in specific regions. Star formation occurs in dense molecular clouds, primarily in the disk of a galaxy. Black hole accretion occurs in the nucleus, where gas can be funneled by gravitational torques. Supernova explosions inject energy and momentum into the interstellar medium, creating superbubbles that can break out of the disk and expel gas into the halo or even into the intergalactic medium. AGN-driven winds, if they are powerful enough, can also expel gas from the entire galaxy, quenching star formation and potentially regulating the growth of the galaxy as a whole. The spatial and temporal coordination of these processes determines the overall evolution of a galaxy, and capturing this coordination requires simulations with sufficient resolution to resolve individual star-forming regions, individual supernovae, and the propagation of shocks and winds through a complex, multi-phase medium. Such simulations are possible for individual galaxies, but they are computationally prohibitive when attempting to simulate the formation of large populations of galaxies over the full volume of the observable universe. As a result, most simulations of the early universe employ resolution that, while impressive by computational standards, is still insufficient to resolve the smallest scales of interest. This necessitates the use of subgrid models, which introduce uncertainty and require calibration against observations. The detection of unexpected galaxies by Webb highlights the limitations of these models and the need for further refinement. But it also underscores the fact that our understanding of galaxy formation is incomplete, that there are aspects of the process that are not yet fully understood or adequately captured in simulations. One must also consider the role of observational biases and selection effects. The galaxies detected by Webb are not a random sample of all galaxies in the early universe, but rather those that are bright enough to be detected given the telescope's sensitivity and the integration times used. Fainter galaxies, which may be more numerous, are not yet observed, and their properties remain uncertain. If the majority of stellar mass in the early universe resides in faint galaxies rather than bright ones, then the detected bright galaxies may be atypical, representing rare peaks in the distribution of galaxy properties rather than the norm. Understanding the relative contributions of bright and faint galaxies to the total stellar mass density, to the ionizing radiation budget, and to the chemical enrichment of the intergalactic medium requires observations across a wide range of luminosities. This is challenging at high redshift, where even relatively bright galaxies appear faint due to their great distance and the dimming effect of the expanding universe. Webb's capabilities, while unprecedented, are still limited, and detecting the faintest galaxies requires extremely long integration times, limiting the area of sky that can be surveyed deeply. Trade-offs between depth and area are inherent to observational astronomy. Deep surveys cover small areas and detect faint objects, providing detailed information about rare or low luminosity populations. Wide surveys cover large areas but detect only brighter objects, providing statistical information about the abundance and clustering of galaxies. Both types of surveys are necessary to build a complete picture of galaxy formation, and both are being pursued with Webb, but the data are still accumulating, and the full census of galaxies at high redshift is not yet available. Even with complete observational coverage, interpreting the data requires careful modeling of the relationship between observed properties and physical quantities. The observed brightness of a galaxy depends not only on its stellar mass and star formation rate, but also on dust extinction, the absorption and scattering of light by dust grains in the interstellar medium. Dust, composed of small particles of carbon, silicon, and other heavy elements, forms in the ejecta of dying stars and in the interstellar medium, and is most effective at absorbing ultraviolet and optical light, re-radiating the absorbed energy in the infrared. In the early universe, the abundance of dust is expected to be lower than in the present day because dust production requires heavy elements, which are produced by stars and gradually accumulate over time. However, even small amounts of dust can have significant effects on the appearance of a galaxy, dimming its ultraviolet emission and making it appear redder than it would otherwise. If early galaxies contained more dust than expected, due to rapid production by supernovae or other processes, then their intrinsic brightness and star formation rates could be higher than inferred from observations, potentially alleviating some of the tension with models. But dust has another effect. It emits in the infrared, and this emission can be detected, providing an independent measure of the dust content and the obscured star formation. Webb is sensitive to infrared wavelengths and can detect dust emission from high redshift galaxies, allowing astronomers to assess the contribution of dust-obscured star formation to the total star formation rate. Early results indicate that some, but not all, high redshift galaxies exhibit significant infrared emission, suggesting that dust is indeed present, but the degree of obscuration varies from galaxy to galaxy. Accounting for dust requires models of dust formation, destruction, and evolution, which add another layer of complexity to simulations. Dust forms in the outflows from dying stars, particularly in the ejecta of supernovae and in the winds from asymptotic giant branch stars, low, to intermediate mass stars in the late stages of their evolution. Once formed, dust grains can grow by accreting gas phase metals from the interstellar medium, or they can be destroyed by shocks from supernovae, by exposure to intense radiation or by collisions with other grains. The balance between formation and destruction determines the dust-to-gas ratio, which in turn affects the extinction and the infrared emission. In the early universe, the dust-to-gas ratio is expected to be low because there has been little time for dust to accumulate. But if star formation rates were high, as the Webb observations suggest, then the production of dust could have been more rapid, allowing dust to build up more quickly than in lower star formation rate environments. This is supported by observations of some high-redshift galaxies that show evidence of dust, but the dust properties, such as grain size, distribution, and composition, may differ from those in the local universe, affecting the interpretation of extinction and emission. The spectral energy distribution, the brightness of a galaxy as a function of wavelength, encodes information about stellar populations, dust content, star formation rate, and the presence of active galactic nuclei. Decomposing the observed spectral energy distribution into these components requires fitting models to the data, models that include assumptions about the star formation history, the initial mass function, the dust properties, and the contribution from AGN. The fitting process is non-unique, meaning that multiple combinations of parameters can produce similar spectral energy distributions, introducing degeneracies and uncertainties in the derived quantities. Breaking these degeneracies requires additional information, such as spectroscopy, which reveals emission and absorption lines that are sensitive to specific physical conditions. Emission lines from ionized gas, such as hydrogen alpha, oxygen-3, and nitrogen-2, indicate the presence of young, hot stars and provide information about the metallicity and ionization state of the gas. Absorption lines from stellar atmospheres indicate the presence of older stellar populations and provide information about the ages and metallicities of stars. The combination of photometry, broadband brightness measurements, and spectroscopy allows for more robust determinations of galaxy properties. But spectroscopy is more time-consuming and requires longer integration times, especially for faint objects at high redshift. Webb is conducting spectroscopic surveys of high-redshift galaxies, and the data are revealing details about their physical conditions, chemical compositions, and kinematics. Emission line ratios indicate that some early galaxies have metallicities that are a significant fraction of the solar metallicity, higher than expected for galaxies observed only a few 100 million years after the Big Bang. This supports the inference from broadband observations that these galaxies have experienced rapid chemical enrichment, but it also deepens the puzzle of how such enrichment occurred so quickly. The kinematics of gas within these galaxies, measured from the widths and shifts of emission lines, indicate that some exhibit ordered rotation, suggestive of disk-like structures, while others show more chaotic motions, indicative of mergers or turbulent gas flows. The presence of ordered rotation at early times suggests that angular momentum has been efficiently transferred from the large-scale environment to the galaxy, and that the gas has settled into a rotationally supported disk. This is expected to occur as gas cools and loses pressure support, but the timescale for this process depends on the cooling rate and the rate of gas accretion, both of which are uncertain at early times. Mergers, on the other hand, disrupt ordered structures, stirring the gas and stars and redistributing angular momentum. Major mergers, where two galaxies of comparable mass collide, can trigger intense bursts of star formation by funneling gas to the center, and they can also feed the central black hole, triggering AGN activity. Minor mergers, where a smaller galaxy is accreted by a larger one, have less dramatic effects but still contribute to the growth of the host galaxy. The frequency and impact of mergers at high redshift depend on the number density of galaxies and the rate at which they encounter each other, which in turn depends on the clustering of dark matter halos and the efficiency with which halos form galaxies. Clustering measurements, which quantify the tendency of galaxies to be found near other galaxies, provide information about the dark matter halos in which galaxies reside and about the processes that link galaxy formation to halo assembly. In the Standard Model, galaxies are more strongly clustered if they reside in more massive halos, because massive halos are biased tracers of the underlying dark matter distribution, preferentially forming in regions where the initial density of dark matter was higher. By measuring the clustering of high-redshift galaxies, astronomers can infer the typical halo masses and assess whether the observed galaxies are consistent with expectations from simulations. Early measurements of galaxy clustering at high redshift suggest that the detected galaxies reside in relatively massive halos, consistent with their high luminosities and inferred stellar masses. But the number density of such halos at early times is limited by the time available for gravitational collapse, and if the observed galaxies are more abundant than the halos that should host them, this would indicate a tension in the hierarchical structure formation paradigm. The hierarchical model, in which structures form from the bottom up, with small halos merging to form larger ones, is a direct consequence of the cold dark matter scenario and is well supported by observations at later times. But extrapolating this model to the earliest times assumes that the physics governing structure formation remains the same, that there are no new processes or phases of cosmic evolution that alter the growth of perturbations. If dark matter has properties not accounted for in the standard model, or if there are interactions between dark matter and other components of the universe, the formation of structure could have proceeded differently at early times. Alternative dark matter models, such as warm dark matter or self-interacting dark matter, have been proposed to address other observational issues, such as the apparent deficit of satellite galaxies around the Milky Way or the core density profiles observed in some dwarf galaxies. These models predict different halo mass functions and different internal structures for halos, which could affect the formation and properties of the galaxies they host. However, these models are tightly constrained by observations at later times, and their effects on early galaxy formation are not necessarily sufficient to resolve the tension with Webb observations. Another class of models involves modifications to the theory of gravity itself. General relativity has been tested extensively in the solar system, in binary pulsar systems, and through the detection of gravitational waves from merging black holes and neutron stars, and it has passed all tests with high precision. However, its applicability on cosmological scales, particularly in the presence of dark matter and dark energy, is less certain. Modified gravity theories, such as MOND, modified Newtonian dynamics, or theories involving extra dimensions, attempt to explain observations attributed to dark matter and dark energy through changes to the gravitational force law rather than through the introduction of new matter and energy components. These theories generally struggle to simultaneously explain the wide range of observations that dark matter and dark energy can account for, from the rotation curves of galaxies to the large-scale structure of the universe to the cosmic microwave background. Moreover, they often make specific predictions that differ from general relativity in observable ways, and these predictions are increasingly being tested with high-precision observations. To date, no modified gravity theory has proven as successful as the standard model in explaining the full range of cosmological and astrophysical observations. Thus, while it is always prudent to remain open to the possibility that our fundamental theories may need revision, the weight of evidence currently favors the standard cosmological model, and the challenge posed by Webb's observations is more likely to lie in our understanding of the astrophysical processes of galaxy formation rather than in the underlying physics of gravity or dark matter. This brings us back to the question of what, specifically, is missing from current models of galaxy formation. Is it a more accurate treatment of star formation and feedback? A better understanding of the initial mass function in metal-free environments? A more detailed accounting of the role of magnetic fields, turbulence, and cosmic rays? Or is it something more fundamental, a process or phase of evolution that has not yet been considered? One possibility that has been discussed in the literature is the role of dark matter annihilation or decay. If dark matter particles annihilate or decay, they release energy that can heat the surrounding gas, affecting its ability to cool and collapse into stars. In the early universe, when dark matter densities were higher, the rate of annihilation or decay would have been greater, potentially injecting significant amounts of energy into the gas and altering the thermal history of the universe. This could delay the formation of the first stars, or it could affect the efficiency of subsequent star formation by keeping gas at higher temperatures. However, the amount of energy released depends on the properties of the dark matter particle, its mass and interaction cross-section, and current constraints from observations of the cosmic microwave background and from indirect searches for dark matter annihilation products place strict limits on these properties. Within these limits, the effects of dark matter annihilation or decay are generally too small to significantly alter the formation of galaxies. Those subtle effects may be present and could be tested with increasingly precise observations. Another exotic possibility involves the role of primordial black holes that formed in the very early universe from the collapse of density perturbations rather than from the death of stars. If a significant fraction of dark matter consists of primordial black holes, they could affect structure formation by providing additional seeds for the growth of supermassive black holes, or by altering the dynamics of gas through gravitational interactions. However, observational constraints on the abundance of primordial black holes are stringent, and they can only comprise a small fraction of the dark matter without violating limits from gravitational lensing, cosmic microwave background observations, and the distribution of large-scale structure. Thus, while exotic scenarios can be imagined, they are generally disfavored by existing observations, and the most likely explanation for the galaxies observed by Webb lies within the framework of standard astrophysics, albeit with processes that are not yet fully understood or accurately modeled. One area that has received increasing attention is the role of the high redshift universe's environment itself. The intergalactic medium in the early universe was denser and more metal-poor than it is today, and the radiation background was dominated by the hard ultraviolet and X-ray emission from the first stars and black holes rather than the softer spectrum of the present-day universe. This radiation background affects the ionization state and temperature of the gas, influencing its ability to cool and form structures. In particular, the Lyman-Werner background, ultraviolet radiation capable of dissociating molecular hydrogen, can suppress the formation of low-mass galaxies by preventing gas from cooling in small halos. If the Lyman-Werner background in the early universe was stronger than expected, perhaps due to the presence of more early stars or more luminous quasars, it could have suppressed star formation in small halos, while allowing it to proceed more efficiently in larger halos where the gas is denser and cooling can occur through other mechanisms. This would shift the galaxy population toward higher masses, consistent with the observation of bright, massive galaxies at high redshift. But the Lyman-Werner background itself depends on the number and properties of early stars and galaxies, creating another feedback loop. More stars produce more Lyman-Werner radiation, which suppresses further star formation in small halos, which reduces the number of faint galaxies, which may or may not reduce the overall ionizing radiation budget, depending on the relative contributions of faint and bright galaxies. Disentangling these effects requires self-consistent models that simultaneously track the formation of stars, the emission of radiation, the propagation of that radiation through the intergalactic medium, and the response of the gas to the changing radiation field. Such models are computationally challenging, requiring radiative transfer calculations that account for the absorption, scattering, and emission of radiation at every point in space, coupled to hydrodynamic simulations that track the motion and thermodynamic state of the gas. Approximate methods, such as post-processing simulations to calculate radiative transfer after the fact, or using simplified prescriptions for the radiation field, are often employed, but they introduce uncertainties and may miss important coupling between the radiation field and the dynamics of the gas. The increasing availability of computational resources and the development of more efficient algorithms are gradually making it feasible to perform fully coupled simulations, and these are beginning to provide insights into the detailed processes that govern early galaxy formation. However, even with perfect simulations, the interpretation of observations requires accurate models of how physical quantities translate into observables, how stellar spectra, dust emission, and gas emission combine to produce the spectral energy distributions that telescopes detect. Stellar population synthesis models, which calculate the integrated light from a population of stars given assumptions about their ages, metallicities, and initial mass function, are a critical tool in this translation. These models rely on stellar evolution theory, which predicts how stars of different masses change over time, burning through their nuclear fuel and evolving through different stages. The light from a galaxy is the sum of the light from all of its stars, weighted by the number of stars at each age and mass, and different star formation histories produce different spectral shapes. Young stellar populations, dominated by massive, short-lived stars, are blue and luminous, with strong emission lines from ionized gas heated by the star's ultraviolet radiation. Old stellar populations, dominated by low-mass, long-lived stars, are red and fainter, with absorption lines from stellar atmospheres but little emission from gas. By fitting observed spectral energy distributions and spectra with models that include a range of stellar ages and metallicities, astronomers can infer the star formation history and chemical enrichment history of a galaxy. But these inferences are only as accurate as the underlying models and stellar evolution theory, while well-tested for stars in the present-day universe, is less certain for metal-free stars or for stars with unusual compositions. The atmospheres of metal-free stars, for example, lack the opacity sources provided by heavy elements, affecting their temperatures, luminosities, and spectra. The nuclear reaction rates in the cores of metal-free stars may also differ from those in metal-rich stars, affecting their lifetimes and the yields of heavy elements they produce when they die. Similarly, the initial mass function, the distribution of masses with which stars form, is a key ingredient in stellar population synthesis models, but its form is not derived from first principles. It is instead inferred from observations of nearby, star-forming regions and applied universally, with the assumption that the physical processes that determine stellar masses, such as the fragmentation of molecular clouds and the accretion of gas onto protostars, are similar across different environments. But there is no strong theoretical reason to expect the initial mass function to be universal, and it could vary with the metallicity, density, temperature, or turbulence of the gas from which stars form. If the initial mass function in the early universe was different from that in the present day, the integrated light from early galaxies would differ from model predictions, potentially explaining some of the observed discrepancies. A top-heavy initial mass function, with more massive stars relative to low-mass stars, would make galaxies more luminous per unit stellar mass, and would produce more heavy elements per generation of stars, both of which are consistent with the Webb observations. But a top-heavy initial mass function would also alter the shapes of spectral energy distributions in specific ways, enhancing the ultraviolet emission and reducing the red and infrared emission, and these predictions can be tested against observations. Current spectroscopic and photometric data from Webb are being analyzed to search for evidence of variations in the initial mass function, but the results are not yet conclusive. Some studies find marginal evidence for a top-heavy initial mass function in certain high-redshift galaxies, while others find consistency with a standard initial mass function. The uncertainties in the data, combined with the degeneracies in the models, make it difficult to draw firm conclusions, and more observations, particularly deep spectroscopy covering a wide range of wavelengths, are needed. Another source of uncertainty lies in the treatment of nebular emission, the light emitted by ionized gas in star-forming regions. Young, massive stars emit copious ultraviolet radiation, which ionizes the surrounding hydrogen and other elements, creating HI regions where the gas is hot and emits characteristic emission lines. These lines, such as hydrogen alpha, hydrogen beta, and lines from ionized oxygen, nitrogen, and sulfur, can contribute significantly to the total light from a galaxy, particularly in the rest frame optical and near-infrared wavelengths, which, due to redshift, are observed by Webb in the mid-infrared. Nebular emission depends on the ionizing photon production rate, which is related to the star formation rate and the initial mass function, and on the properties of the gas, such as its density, temperature, and metallicity. Higher metallicities lead to more efficient cooling through metal lines, increasing the strength of certain emission lines, while lower metallicities reduce cooling and alter the ionization balance. The detailed shape of the emission line spectrum thus encodes information about both the stellar populations and the gas, and modeling it accurately is essential for interpreting observations. Nebular emission models have been developed and refined over decades, but they rely on atomic data, the transition probabilities and cross-sections for various processes, which are determined through laboratory experiments and quantum mechanical calculations. For some ions and transitions, particularly those involving highly ionized species or complex atoms, the atomic data are incomplete or uncertain, introducing additional uncertainties into the models. Efforts to improve atomic data and to incorporate more detailed physics into nebular emission models are ongoing, and these improvements are critical for maximizing the scientific return from Webb observations. The presence of active galactic nuclei adds yet another layer of complexity. AGN emit across the entire electromagnetic spectrum, from radio waves to gamma rays, with spectral shapes that differ from those of stars. The ultraviolet and optical emission from the accretion disk around the black hole is characterized by a blue continuum and broad emission lines, where broad refers to the high velocities of gas near the black hole, up to thousands or even tens of thousands of kilometers per second. The X-ray emission, produced by the hot corona above the accretion disk, is hard and luminous, capable of ionizing gas at large distances from the black hole. Infrared emission from AGN can come from dust heated by the intense radiation, forming a dusty torus or disk that obscures the central regions when viewed edge-on, but is visible when viewed face-on or at intermediate angles. The relative contributions of stellar and AGN emission to the total light from a galaxy depend on the luminosity of the AGN, the orientation of the system, and the degree of obscuration by dust. Distinguishing between these contributions is essential for determining the star formation rate and the black hole accretion rate, both of which are key to understanding the coevolution of galaxies and their central black holes. Webb's infrared sensitivity allows it to detect emission from dust-obscured AGN, and its spectroscopic capabilities can identify AGN through their characteristic broad emission lines or through the detection of high ionization lines that require the intense radiation fields produced only by accretion onto black holes. Early results indicate that some high redshift galaxies do host active galactic nuclei, confirming that supermassive black holes were already in place and growing at early times. The fraction of galaxies hosting AGN and the typical luminosities of these AGN provide constraints on the seed black hole masses and the efficiency of black hole growth. If a significant fraction of the light from early galaxies comes from AGN rather than stars, then the inferred star formation rates would be overestimated, potentially resolving part of the tension with models. However, the spectroscopic signatures of AGN are distinct, and while some galaxies show clear AGN signatures, many of the bright, high redshift galaxies detected by Webb do not, indicating that their light is dominated by stars. Thus, while AGN contribute to the overall picture, they do not appear to be the primary explanation for the observed abundance of bright galaxies. The synthesis of all these considerations, dark matter halos, gas cooling and accretion, star formation and feedback, chemical enrichment, dust production and extinction, nebular emission, black hole growth and AGN feedback, magnetic fields, turbulence, and cosmic rays, paints a picture of galaxy formation as an extraordinarily complex process, one that involves a vast range of physical scales and a multitude of interacting processes. No single adjustment to a single parameter is likely to fully reconcile the Webb observations with existing models. Instead, what is required is a comprehensive reevaluation of how these processes operate in the early universe, informed by the new data Webb is providing. This reevaluation is already underway. Theorists are revisiting assumptions about star formation efficiency, exploring the consequences of variations in the initial mass function, refining models of dust formation and radiative transfer, and developing more sophisticated treatments of feedback. Observers are conducting follow-up studies of the galaxies detected by Webb, obtaining deeper spectra, searching for fainter companions, and measuring the clustering and large-scale environment of these systems. The interplay between theory and observation, each informing and challenging the other, is driving progress toward a more complete understanding of how the first galaxies formed. Yet even as progress is made, the fundamental question remains: does the light detected by Webb truly come from a time that should not permit the existence of such objects? The answer hinges on the meaning of should not. If should not refers to the predictions of models calibrated on observations of the later universe, then yes, the light is unexpected. But models are approximations, simplified representations of reality that cannot capture every detail of the physical processes at work. The fact that observations exceed predictions does not necessarily imply a crisis in cosmology, but rather an opportunity to refine and improve the models. If, on the other hand, should not refers to the fundamental constraints imposed by the age of the universe, the speed of light, and the laws of physics, then the situation is more profound. The age of the universe at a given redshift is determined by the expansion history, which is in turn determined by the energy content of the universe. If the energy content is different from what we infer, if dark energy or dark matter behaves differently than assumed, or if there's an additional component that we have not accounted for, then the age at a given redshift could be different, and the time available for galaxy formation could be longer or shorter. But changing the energy content of a universe has wide-ranging consequences. Dark energy affects the expansion rate at late times, when the universe is old and structures have already formed, and its influence at early times is negligible. Dark matter affects structure formation directly, and changing its properties alters the formation of halos, the clustering of galaxies, and the dynamics of groups and clusters. These effects are observable and are constrained by data from multiple independent sources, from the cosmic microwave background to the distribution of galaxies to gravitational lensing. Introducing a new component, such as an additional form of dark energy that is significant at early times, or a new interaction between dark matter and radiation, would need to explain not only the Webb observations, but also all of the other observations that the standard model already explains. This is a high bar to meet, and proposals for such modifications are subject to rigorous scrutiny and testing. To date, no such modification has been shown to be both necessary and consistent with all available data. Thus, the most likely resolution to the puzzle posed by Webb observations lies not in revising the fundamental cosmological framework, but in deepening our understanding of the astrophysical processes within that framework. The early universe was a different place, with different physical conditions, and the processes that govern galaxy formation may have operated more efficiently or in different ways than they do today. Capturing this in models requires not just more computing power or better algorithms, but also new insights into the physics of gas, stars, and black holes under the extreme conditions of the early universe. One aspect that is beginning to receive more attention is the role of the first stellar populations in setting the stage for subsequent galaxy formation. Population 3 stars, as discussed, were massive, metal-free, and short-lived, but their influence extended far beyond their brief existence. Their ultraviolet radiation ionized large volumes of gas, creating ionized bubbles that expanded into the neutral intergalactic medium. Their supernova explosions dispersed heavy elements, enriching the surrounding medium and altering the conditions for the next generation of star formation. Their remnants, black holes and neutron stars, contributed to the population of compact objects and may have served as seeds for supermassive black holes. The spatial distribution and timing of population 3 star formation are key factors in determining how quickly subsequent generations of stars could form and how efficiently galaxies could assemble. If population 3 stars formed in a clustered fashion, with many stars igniting in close proximity within a short time, their combined feedback could have been powerful enough to expel gas from their host halos, suppressing further star formation locally, but enriching the surrounding medium and seeding nearby halos with metals. If, instead, population 3 stars formed more sporadically, scattered across different halos, their individual impacts would have been smaller, allowing star formation to proceed more continuously. Simulations of population 3 star formation are challenging because they require resolving the collapse of gas clouds down to stellar scales, following the complex chemistry of molecular hydrogen formation and destruction, and tracking the radiation emitted by the stars and its interaction with the surrounding gas. Recent advances in simulation techniques, including adaptive mesh refinement and radiative transfer on the fly, have made it possible to simulate individual population 3-star forming regions in great detail, revealing the conditions under which the first stars ignited and the immediate consequences of their formation. These simulations suggest that population 3 stars likely formed in mini-halos, dark matter halos with masses of around 1 million solar masses, too small to retain gas heated by supernova feedback, but large enough to allow primordial gas to cool through molecular hydrogen and collapse. The first stars in a given mini-halo would have been solitary or formed in small groups, rather than in large clusters, because the gas cloud would have fragmented only once or a few times before the onset of feedback halted further collapse. After the death of the first star or stars, the mini-halo would have been largely evacuated of gas, and subsequent star formation would have occurred in nearby halos that accreted the metal-enriched ejecta. Over time, as more and more mini-halos formed stars and dispersed metals, the intergalactic medium became progressively enriched, and the transition from population 3 to population 2 star formation occurred. Population 2 stars, which form from gas with at least trace amounts of heavy elements, can be less massive and longer-lived than population 3 stars, and their formation is more similar to that of stars in the present-day universe. The transition from one population to the other is not sharp but gradual, and the exact metallicity threshold at which the transition occurs depends on the cooling mechanisms available and the fragmentation behavior of the gas. This transition is critical for the formation of the first galaxies because it marks the shift from inefficient, isolated star formation in mini-halos to more sustained star formation in larger halos that can retain gas and build up stellar populations over time. The galaxies detected by Webb are well past this transition, showing evidence of multiple generations of stars and significant chemical enrichment. But the rapidity with which they reached this state suggests that the transition occurred early and that the subsequent star formation was highly efficient. Understanding this efficiency requires understanding not just the formation of stars, but also the retention of gas within galaxies. Supernova feedback, as noted, can expel gas from halos, particularly from low-mass halos where the gravitational potential is shallow. But the efficiency of gas expulsion depends on the coupling between the supernova energy and the gas, which in turn depends on the density and temperature structure of the interstellar medium. If the gas is clumpy, with dense clouds embedded in a diffuse medium, supernova explosions may primarily heat the diffuse medium, driving winds that escape the galaxy, while leaving the dense clouds relatively unaffected, allowing star formation to continue within them. This picture of a multi-phase interstellar medium, with gas existing in a range of densities and temperatures, is well established for galaxies in the present-day universe, but its applicability to early galaxies is less clear. The cooling mechanisms available in metal-poor gas are limited, making it more difficult to maintain a cold, dense phase, and the intense radiation from massive stars could ionize and heat the gas, homogenizing the density structure. On the other hand, rapid star formation could produce overlapping supernova remnants, creating a network of shocks and compressed regions where dense clouds could form and persist despite the hostile environment. The balance between star formation and feedback, and the resulting retention or expulsion of gas, determines the mass growth rate of a galaxy and its observable properties. If feedback is too strong, star formation is suppressed, and the galaxy remains small and faint. If feedback is too weak, star formation proceeds unchecked, consuming the gas supply rapidly and producing a bright burst of star formation that may not be sustainable over long periods. The observed properties of high-redshift galaxies, bright but not implausibly so, suggest a delicate balance, one that allows for high star formation rates without completely evacuating the gas reservoir. Achieving this balance in simulations requires careful tuning of the subgrid models that govern star formation and feedback, and it is here that much of the current effort is focused. Different simulations employ different prescriptions, some tying star formation directly to gas density, others incorporating explicit models of molecular cloud formation and turbulent regulation, still others treating star formation stochastically to account for the random nature of the collapse and fragmentation process. Similarly, feedback models range from simple thermal energy injection to sophisticated treatments of momentum-driven winds, radiation pressure, and cosmic ray acceleration. The diversity of approaches reflects the inherent uncertainty in how these processes operate on unresolved scales, and the goal is not to find a single correct model, but to explore the range of possibilities and identify which models are consistent with observations. The Webb data provide critical new benchmarks for this exploration, revealing properties of early galaxies that must be reproduced by any successful model, and thereby narrowing the range of viable prescriptions. Beyond the internal processes within galaxies, the external environment also plays a role. Galaxies do not form in isolation, but within the cosmic web, the network of filaments and nodes formed by the gravitational collapse of dark matter. Gas flows along these filaments, accreting onto galaxies and fueling star formation, and galaxies that reside at the intersections of filaments in the densest regions of the web receive more gas and grow more rapidly. The structure of the cosmic web at high redshift is determined by the initial conditions set during inflation and by the subsequent growth of perturbations under gravity, and it is a key factor in determining where and when the first galaxies form. Observations of the large-scale distribution of galaxies at high redshift through wide-area surveys provide information about the cosmic web and allow comparisons with simulations. Early results from Webb, combined with ground-based surveys, indicate that high-redshift galaxies are clustered, residing in overdense regions that will eventually collapse to form massive galaxy clusters in the present-day universe. This is consistent with expectations, but the degree of clustering and the typical separations between galaxies provide additional constraints on the formation timescales and the efficiency of star formation in different environments. Galaxies in dense regions may experience more frequent interactions and mergers, accelerating their growth, but they may also be subject to environmental effects such as ram pressure stripping, where the hot gas in the environment strips cold gas from the galaxy as it moves through the intergalactic medium, or tidal interactions, where the gravitational pull of nearby galaxies distorts and disrupts the galaxy's structure. These effects are more important at later times, when the densities are higher and the velocities are greater, but they may also be relevant in the early universe, particularly in the densest protocluster environments. The interplay between internal processes, such as star formation and feedback, and external processes, such as gas accretion and environmental effects, determines the final properties of a galaxy and its evolutionary trajectory. Disentangling these effects requires both observations of individual galaxies and statistical studies of galaxy populations, examining how properties vary with environment, with redshift, and with galaxy mass. Webb is uniquely positioned to contribute to both types of studies. Its sensitivity allows it to detect and characterize individual high redshift galaxies in unprecedented detail, revealing their stellar masses, star formation rates, chemical compositions, and internal kinematics. Its field of view, while smaller than that of ground-based wide-field surveys, is sufficient to study the environments of these galaxies, identifying companions, satellites, and nearby structures that may influence their evolution. Combining Webb data with data from other facilities, such as the Atacama Large Millimeter Array, which observes the cold gas and dust in galaxies, or the upcoming Vera Rubin Observatory, which will conduct a deep, wide-area survey of the optical sky, will provide a comprehensive view of galaxy formation across cosmic time. As more data accumulate, patterns are beginning to emerge. Some high-redshift galaxies appear to be isolated, residing in relatively low-density regions of the cosmic web, while others are found in groups or protoclusters, surrounded by companions. Some show signs of ongoing star formation, with blue colors and strong emission lines, while others appear more quiescent, with redder colors and weaker emission, suggesting that star formation has been suppressed or has recently ceased. The diversity of properties indicates that there is no single pathway for galaxy formation in the early universe, but rather a range of trajectories determined by the mass of the dark matter halo, the efficiency of gas accretion, the star formation history, and the impact of feedback and environment. Understanding this diversity and the physical processes that drive it is the central challenge of galaxy formation theory. It requires not just modeling individual processes in isolation, but capturing the complex interplay between them, accounting for the feedbacks and couplings that link star formation to black hole growth, gas cooling to heating, and internal dynamics to external environment. It requires simulations that span a vast range of scales, from the cosmological scales on which dark matter halos form to the scales of individual stars and black holes where the key physical processes occur. And it requires observations that probe all aspects of galaxy properties, from their integrated light to their resolved structures, from their gas content to their stellar populations, from their chemical compositions to their kinematics. The James Webb Space Telescope is providing a wealth of such observations, and the data are being scrutinized by researchers around the world, analyzed with sophisticated tools, and compared with simulations to test and refine our understanding. Each new dataset brings new insights, revealing details that were previously hidden by the limitations of earlier telescopes, and each new insight raises new questions, pushing the frontiers of knowledge further. One of the most intriguing aspects of the Webb observations is the sheer number of bright galaxies detected at high redshift. Early predictions, based on pre-Webb models, suggested that such galaxies should be rare, with only a handful detectable in the areas of sky surveyed. Instead, Webb is finding them in abundance, with number densities that exceed predictions by factors of several. This overabundance, if confirmed by further observations and analyses, would indicate that something fundamental is missing from the models, something that enhances the efficiency of galaxy formation in the early universe. Possible explanations range from the plausible to the speculative. On the plausible end, it could be that star formation efficiency was simply higher than assumed, allowing galaxies to convert a larger fraction of their gas into stars in a given time. This is a straightforward adjustment, but as discussed, it must be done carefully to avoid creating new tensions with other observations. Alternatively, the initial mass function could have been skewed toward more massive stars, making galaxies more luminous without requiring more total stellar mass. This too is plausible, but requires evidence from spectroscopy to confirm. On the more speculative end, there could be astrophysical processes at work that are not included in standard models. For example, if there were a population of very massive stars, more massive than any observed in the present-day universe, they could have contributed significantly to the light from early galaxies while leaving little trace in their remnants, as such stars would have collapsed directly to black holes without producing supernovae. Or there could be processes that enhance the merger rate of galaxies in the early universe, accelerating their growth beyond what hierarchical models predict. Each of these ideas has merit, but each also requires testing against observations to determine whether it is consistent with a full range of data. The detection of light from these early galaxies is not simply a matter of seeing something unexpected. It is a window into the conditions of the universe at a time when it was fundamentally different from today. The gas was hotter and denser. The radiation background was harder and more intense. The dark matter halos were smaller and more numerous, and the chemical composition was simpler. Stars and galaxies were forming for the first time, setting in motion the processes that would shape the universe we see today. Understanding this epoch, known as the epoch of reionization and the era of the first galaxies, is one of the primary science goals driving modern observational cosmology. Reionization, the process by which the neutral hydrogen filling the universe was ionized by radiation from the first stars and galaxies, marks a phase transition in cosmic history. Before reionization, the universe was opaque to ultraviolet light, as any ultraviolet photon emitted by a star would be quickly absorbed by neutral hydrogen. After reionization, the universe became transparent, allowing ultraviolet light to travel freely across cosmic distances. The transition from opacity to transparency is not instantaneous but gradual, occurring over hundreds of millions of years, and its timing and duration depend on the properties and abundance of the sources of ionizing radiation. The sources are primarily stars, particularly massive stars that emit ultraviolet photons capable of ionizing hydrogen. But active galactic nuclei also contribute, especially at later stages of reionization. The efficiency with which these sources produce ionizing photons and the fraction of those photons that escape from their host galaxies into the intergalactic medium determine the rate at which reionization proceeds. Higher efficiency and higher escape fractions lead to faster reionization, while lower values slow the process. Observations of the cosmic microwave background constrain the overall timing of reionization through the measurement of optical depth, which quantifies the amount of scattering of microwave photons by free electrons produced during reionization. The optical depth measured by the Planck satellite indicates that reionization was largely complete by a redshift of around 6, with the midpoint occurring at a redshift of around 8, corresponding to an age of the universe of about 600 million years. This is consistent with observations of distant quasars and the spectra of high redshift galaxies, which show that the intergalactic medium transitions from mostly neutral to mostly ionized over this redshift range. But the details of reionization, the spatial distribution of ionized regions, the sizes and shapes of the ionized bubbles, and the relative contributions of different sources are still being worked out. Webb's observations of galaxies at the redshifts corresponding to the reionization epoch provide crucial information about the sources responsible for ionizing the universe. By measuring the number, luminosity, and spectral properties of these galaxies, astronomers can estimate the total ionizing photon production rate and compare it to the rate required to reionize the universe within the observed timescale. Early results suggest that galaxies alone can provide sufficient ionizing photons to drive reionization, without requiring a significant contribution from active galactic nuclei, but the escape fraction of ionizing photons from galaxies is a key uncertainty. Ultraviolet photons produced in star-forming regions can be absorbed by dust or neutral gas within the galaxy before they escape into the intergalactic medium, and the fraction that escapes depends on the geometry and density structure of the gas, the distribution of dust, and the intensity of feedback that clears channels through which photons can escape. Measuring the escape fraction directly is difficult because the ionizing photons, at wavelengths shorter than the Lyman limit, are absorbed by intervening neutral hydrogen along the line of sight, making it impossible to detect them from distant galaxies. Instead, astronomers use indirect methods, such as measuring the ratio of ionizing to non-ionizing ultraviolet light in nearby galaxies, or looking for spectral signatures of ionized gas outflows that could indicate channels for photon escape. These methods have uncertainties, and the escape fraction may vary from galaxy to galaxy and with cosmic time, complicating the interpretation of reionization constraints. The galaxies detected by Webb at high redshift provide a new sample for studying escape fractions. Some of these galaxies show signs of intense star formation and strong emission lines, which could indicate conditions favorable for high escape fractions. Others show more compact morphologies or evidence of dust, which could reduce escape fractions. By analyzing the properties of a large sample of high redshift galaxies and comparing with models of reionization, astronomers can refine estimates of the typical escape fraction and assess whether the observed galaxy population is sufficient to drive reionization. Reionization is not the only process shaping the early universe. The buildup of chemical elements, the growth of magnetic fields, the production and dispersion of dust, and the formation of the first supermassive black holes all occurred during this epoch, and each of these processes left an imprint on the properties of galaxies that can be observed today. Chemical enrichment, as discussed, requires multiple generations of stars, and the detection of heavy elements in high redshift galaxies provides direct evidence that this enrichment occurred rapidly. The abundances of different elements, measured from spectroscopic observations, provide clues to the types of stars that produce them and the timescales over which enrichment occurred. For example, oxygen and carbon are produced in different types of stars and on different timescales. Oxygen is produced primarily in massive stars and is dispersed by core collapse supernovae, which occur within a few million years of star formation. Carbon is produced in intermediate mass stars and is dispersed later, as these stars reach the end of their lives and shed their outer layers through stellar winds. The ratio of oxygen to carbon in a galaxy thus provides information about the relative contributions of different stellar populations and the time elapsed since the onset of star formation. Observations of high-redshift galaxies show a range of oxygen-to-carbon ratios, indicating that the enrichment histories vary from galaxy to galaxy. Some galaxies have ratios consistent with enrichment dominated by massive stars, suggesting very young stellar populations, while others have ratios that require contributions from intermediate mass stars, suggesting ages of tens of millions of years or more. These variations reflect the diversity of star formation histories and the influence of factors such as gas accretion rate, feedback efficiency, and merger history. The presence of dust in high-redshift galaxies, inferred from infrared emission or from the reddening of stellar light, indicates that dust production also began early. Dust forms in the ejecta of dying stars and in the interstellar medium through the condensation of gas-phase metals onto grain cores, and its abundance increases over time as more stars die and disperse heavy elements. The detection of dust at redshifts of 7 or higher, corresponding to ages of less than a billion years, implies that dust production was efficient, possibly aided by rapid formation in the ejecta of supernovae or by growth in dense molecular clouds. Dust has significant effects on the appearance and evolution of galaxies. It absorbs ultraviolet and optical light from stars, converting it to infrared emission, and it provides a surface for chemical reactions that form molecules such as molecular hydrogen and carbon monoxide, which are crucial for cooling and star formation. The presence of dust at early times thus has implications for the star formation rates, the observability of galaxies, and the chemical evolution of the interstellar medium. Magnetic fields, though more difficult to observe, also play a role. They provide additional pressure support in the interstellar medium, affecting the stability and collapse of gas clouds. They channel gas flows and influence the propagation of cosmic rays, which are high-energy particles accelerated in supernova shocks and other energetic events. Cosmic rays, in turn, can heat the gas through collisions, providing an additional source of feedback that regulates star formation. The strength and structure of magnetic fields in high-redshift galaxies are not yet well constrained, but theoretical models suggest that they could be amplified rapidly through dynamo processes driven by turbulence and differential rotation. The formation of supermassive black holes at early times, as evidenced by the detection of active galactic nuclei and the inferred masses from galaxy dynamics, is another key aspect of this epoch. The mechanisms by which these black holes form, whether from the collapse of the first stars, from direct collapse of massive gas clouds, or from the runaway growth of stellar clusters, are still debated, and each mechanism predicts different observational signatures. Distinguishing between these scenarios requires observations of the host galaxies, the environments in which the black holes reside, and the properties of the black holes themselves, such as their masses and accretion rates. Webb's spectroscopic capabilities allow for the identification of active galactic nuclei through their characteristic broad emission lines and high ionization features, and for the measurement of black hole masses through the kinematics of the gas in the vicinity of the black hole or through correlations between black hole mass and galaxy properties. Early results indicate a range of black hole masses, from millions to billions of solar masses, at redshifts where the universe was less than 1 billion years old. These masses imply rapid growth, as discussed, and understanding how such growth was achieved is an active area of research. One possibility is that the early universe contained a population of seed black holes that were more massive than those formed from the collapse of individual stars. If these seeds had masses of thousands or tens of thousands of solar masses, the time required to grow to supermassive scales would be reduced, potentially explaining the observed population. But forming such massive seeds requires special conditions, as noted, and whether these conditions were common enough to account for the observed number of supermassive black holes is uncertain. Another possibility is that black hole growth in the early universe was sustained at or above the Eddington limit for extended periods. The Eddington limit is typically thought to be a strict upper bound on accretion rate, but under certain conditions, such as super Eddington accretion flows with strong outflows, black holes can accrete at rates higher than the Eddington limit without being choked off by radiation pressure. Simulations of such flows suggest that they can occur when the gas supply is abundant and the accretion is geometrically thick, with radiation being advected into the black hole rather than escaping, allowing the black hole to grow more rapidly than in standard thin disk models. The relationship between black hole growth and galaxy growth, known as coevolution, is a central theme in modern astrophysics. Observations of the present-day universe reveal tight correlations between black hole mass and properties of the host galaxy, such as the stellar mass or the velocity dispersion of stars in the galaxy's bulge. These correlations suggest that the growth of the black hole is linked to the growth of the galaxy, possibly through feedback mechanisms that regulate both. AGN-driven winds can expel gas from a galaxy, suppressing star formation and limiting the growth of both the black hole and the stellar population, creating a self-regulating system. The detection of supermassive black holes at early times provides an opportunity to study the origins of this coevolution, to determine whether the correlations are already in place at high redshift or whether they emerge later, and to understand the physical processes that link black holes and galaxies. Early results from Webb suggest that the correlations may already be present, with black hole masses roughly consistent with expectations based on the stellar masses of their host galaxies, but the scatter in these correlations is large, and the sample sizes are still small. More observations are needed to draw firm conclusions. The accumulated evidence from Webb, spanning bright galaxies, chemical enrichment, dust, supermassive black holes, and the reionization process, paints a picture of an early universe that was remarkably active and complex. Within the first few 100 million years after the Big Bang, the universe transitioned from a simple, homogeneous state to a structured, evolving cosmos filled with galaxies, stars, black holes, and the beginnings of the rich chemical tapestry that enables the formation of planets and life. This transformation occurred over a time span that, while long by human standards, is incredibly brief by cosmic standards, and the rapidity of this transformation challenges our understanding of the processes involved. The light detected by Webb, light that has traveled for over 13 billion years to reach us, carries with it information about this transformation. Each photon is a messenger from the early universe, encoding in its wavelength, intensity, and arrival time the conditions under which it was emitted. By collecting and analyzing these photons, astronomers reconstruct the history of the cosmos, piecing together the sequence of events that led from the smooth, featureless state imprinted in the cosmic microwave background to the rich, diverse universe we observe today. But the reconstruction is incomplete. There are gaps in our knowledge, processes that are not fully understood, parameters that are uncertain, and observational limits that prevent us from seeing the faintest and most distant objects. The galaxies detected by Webb are not the first galaxies, but rather the brightest and most massive among the first generation. The true first galaxies, those that formed in the smallest halos and ignited the first stars, are likely too faint to be detected even by Webb, and their properties must be inferred indirectly through their cumulative effects on reionization, on chemical enrichment, and on the light of later generations. Future observations, with Webb and with other facilities, will continue to push the boundaries, detecting fainter objects, probing earlier times, and measuring properties with greater precision. Ground-based telescopes equipped with adaptive optics, such as the extremely large telescope under construction in Chile, will provide complementary observations at optical and near-infrared wavelengths, with spatial resolutions that can resolve the internal structures of distant galaxies. Radio telescopes, such as the Square Kilometer Array, will map the distribution of neutral hydrogen in the early universe, tracing the evolution of the intergalactic medium through reionization. Infrared space missions beyond Webb are being planned, with even greater sensitivity and wider fields of view, designed to survey vast volumes of the early universe and detect the faintest galaxies. Each of these facilities will contribute pieces to the puzzle, and the synthesis of data across wavelengths, across time, and across different observational techniques will gradually fill in the gaps, refining our understanding and revealing new complexities. The process is iterative, with each observation prompting new questions, each question driving new theoretical work, and each theoretical advance suggesting new observations. The cycle continues, propelled by curiosity and by the desire to understand our origins, to know how the universe came to be as it is, and to glimpse the processes that unfolded in the darkness before the first light. The light from the early universe, as detected by Webb, is thus not simply an observational curiosity or a challenge to existing models. It is a profound connection to the past, a tangible link to the epochs when the cosmos was young and the future was yet unwritten. It is a reminder that the universe has a history, that it has evolved and changed over immense spans of time, and that the structures we see around us, the galaxies and stars and planets, were not always present, but emerged through processes that we are only beginning to fully comprehend. In contemplating this light, one confronts the limits of current knowledge and the vastness of what remains unknown. The early universe was a place of extremes, where densities, temperatures, and energies far exceeded anything that can be recreated in terrestrial laboratories. The physics that governed it, while rooted in the same fundamental laws that operate today, played out in regimes where our intuitions, honed on observations of the nearby and the recent, may not apply. Understanding these regimes requires extending theories, testing them against observations, and being willing to revise and refine them as new data arrive. The galaxies observed by Webb, with their unexpected brightness, their chemical maturity, their structural complexity, and their supermassive black holes, are telling us that the early universe was different from what many models predicted. They are not telling us that the universe is older than we thought, or that the laws of physics have changed, but rather that the efficiency of the processes that build galaxies, the conversion of gas into stars, the growth of black holes, the dispersal of heavy elements, was higher than anticipated. They are revealing that the early universe was a more fertile and productive environment for galaxy formation than previously believed, and this revelation demands an explanation. The explanation may lie in subtle adjustments to known processes, in refinements of parameters, in better treatments of feedback and accretion. Or it may require new insights, new physical processes that have not yet been considered, or new ways of thinking about the interactions between dark matter, gas, stars, and black holes. The path forward involves both theoretical innovation and observational diligence, combining creativity in proposing new mechanisms with rigor in testing those mechanisms against the full range of available data. As this work progresses, the picture of the early universe will continue to evolve. What once appeared as a smooth, simple beginning will be revealed in ever greater detail, showing the intricate patterns and fluctuations that seeded the structures we see today. The first galaxies will be placed within the broader context of cosmic evolution, understood not as isolated events, but as part of a continuous process of growth, transformation, and increasing complexity. The light detected by Webb, light from a time that straddles the boundary between the primordial and the formed, will serve as a guide, illuminating the path backward through cosmic history and forward through our understanding. The universe, as seen through the eyes of Webb, is a place where the past is accessible, where photons emitted billions of years ago arrive now, carrying information across unimaginable distances and durations. The detection of these photons, their transformation into data, and the interpretation of that data into knowledge is a testament to human ingenuity and to the power of science to reveal truths that are hidden from direct experience. It is also a reminder of the humility required in the face of the cosmos, the recognition that our models are imperfect, our knowledge incomplete, and our understanding always subject to revision. The light from the early galaxies does not exist in the sense that it comes from objects that are still there as they were. Those galaxies, if they survived and were not disrupted or merged, have long since evolved into forms vastly different from what Webb observes. What we see is a snapshot, a moment frozen in time by the finite speed of light, a glimpse of a stage in cosmic evolution that has passed. The galaxies have aged, their stars have lived and died, new generations have formed, and the structures have grown and transformed. What should not exist, in the framing of current models, are not the galaxies themselves, but the state in which they are observed, the level of development they had achieved at such an early cosmic age. This distinction is important. The challenge is not to the reality of the observations, which are robust and repeatable, but to the models that predicted different outcomes. The universe does not conform to our expectations. Rather, our expectations must conform to the universe, adjusted and refined as observations dictate. The process is ongoing, and the ultimate goal is not to defend a particular model, but to arrive at a model that accurately describes reality, that can predict new observations, and that provides a coherent framework for understanding the cosmos. In this sense, the light detected by Webb is both a challenge and an opportunity. It challenges assumptions and forces reevaluation, but it also provides new data, new constraints, and new insights that will ultimately lead to a deeper and more accurate understanding. The path from observation to understanding is not always direct. It involves false starts, revisions, and a gradual accumulation of evidence that narrows the range of viable explanations. But it is a path that has been traveled many times before in other areas of astronomy and physics, and it is a path that has consistently led to progress. The early universe, as revealed by Webb, is a frontier of current research, a domain where the cutting edge of observational capability meets the limits of theoretical understanding. It is a domain where surprises are expected, where the unexpected is almost routine, because it is a domain that has never been observed in such detail before. As Webb continues to operate, as more data accumulate, and as more galaxies are detected and characterized, the picture will become clearer, the surprises will become less frequent, and the models will converge on a consistent description. But the journey is far from over. Each answer raises new questions. Each new galaxy detected at higher redshift pushes the boundary of the observable universe closer to the Big Bang itself, and each refinement of models reveals new subtleties and complexities that were previously hidden. The detection of light from galaxies that appear too advanced for their cosmic age is a chapter in this ongoing story. A chapter that highlights the dynamism of the early universe and the challenges of reconstructing its history from the faint signals that reach us across billions of years. The galaxies themselves, as they existed when the light was emitted, were not aware of violating any models. They simply were governed by the physics of their time and place, forming stars, accreting gas, enriching their interstellar media, and growing in mass and complexity. The fact that their state of development was more advanced than models predicted is a statement about the models, not about the galaxies. The universe does not consult our equations before deciding how to evolve. It follows the laws of physics, which are what they are, and our task is to discover and understand those laws, to express them in mathematical form, and to use them to make predictions that can be tested against observations. When predictions fail, as they have in the case of the bright high-redshift galaxies detected by Webb, it is an indication that the equations are incomplete or that the parameters within them are not correctly determined. This is not a failure of science, but a normal part of the scientific process, a step in the iterative refinement of knowledge. The models that existed before Webb were the best available at the time, based on the data that were available then, and they were successful in explaining many aspects of galaxy formation. But they were not final, and they were always understood to be provisional, subject to revision as new data became available. Webb has provided those new data, and the revision process is now underway. It will take time, effort, and the collaboration of many researchers across multiple disciplines, but the outcome will be a better understanding of the early universe, a more accurate set of models, and a deeper appreciation of the processes that shape the cosmos. This is how science progresses, through the confrontation of theory with observation, through the willingness to revise and refine, and through the relentless pursuit of consistency between what we predict and what we observe. The light that Webb detects, light that should not exist according to prior expectations, is thus a beacon guiding that revision. It points to areas where the models are deficient, where assumptions need to be questioned, where new physics may need to be incorporated. It challenges researchers to think more carefully about the efficiency of star formation, the nature of the first stars, the growth of black holes, the role of feedback, the impact of environment, and the myriad other factors that influence galaxy evolution. It demands a level of detail and sophistication in modeling that pushes the boundaries of what is computationally feasible, and it requires observations of increasing depth and breadth to test the new models that emerge. In the broader context of cosmology, the Webb observations are part of a larger effort to map the history of the universe from its earliest moments to the present day. This history includes the inflationary epoch, the Big Bang nucleosynthesis, the recombination of electrons and protons to form neutral hydrogen, the dark ages when no stars had yet formed, the ignition of the first stars, the formation of the first galaxies, the reionization of the universe, the assembly of large-scale structure, and the eventual formation of galaxies like our own Milky Way, within which planets and life could arise. Each stage of this history is linked to the others, and understanding one stage requires understanding the stages that came before and after. The detection of unexpectedly bright galaxies at high redshift affects our understanding not only of that specific epoch, but also of the later stages. If galaxies formed more efficiently in the early universe, they would have contributed more ionizing photons to the reionization process, potentially completing it sooner or in a more uniform manner. They would have produced more heavy elements, enriching the intergalactic medium and altering the conditions for subsequent star formation. They would have contained more massive black holes, which could have influenced the formation of large-scale structure through their feedback. Each of these effects propagates forward in time, influencing the evolution of the universe in ways that can be observed in the present day. Thus, reconciling the Webb observations with theory is not just an academic exercise confined to the study of the early universe. It has implications for our understanding of cosmic evolution as a whole. It requires ensuring that the models used to describe the early universe are consistent with models used to describe later epochs, and that the physical processes invoked to explain one set of observations do not contradict other observations. This consistency is a stringent test, and it is one that any successful model must pass. The accumulation of evidence, the refinement of models, and the ongoing interplay between theory and observation are the hallmarks of the scientific endeavor. The James Webb Space Telescope, as the most advanced infrared observatory ever built, is playing a central role in this endeavor, providing data of unprecedented quality and revealing aspects of a universe that were previously inaccessible. The light it detects from the early universe, light that challenges expectations and prompts reevaluation, is a testament to the power of observation to surprise, to inform, and to inspire. It reminds us that the universe is richer and more complex than we often imagine, and that there is always more to learn, more to discover, and more to understand. In the end, the question of whether the light detected by Webb comes from a time that should not exist is a question about the adequacy of our models, not about the nature of time or the validity of the observations. The light is real, the galaxies are real, and the cosmic time at which they existed, as determined by their redshifts and the expansion history of the universe, is as well established as any quantity in cosmology. What is being reevaluated is our understanding of how galaxies form and evolve, the rates at which they accumulate mass, the efficiencies with which they convert gas into stars, and the timescales over which chemical enrichment and structural complexity develop. These are astrophysical questions, rooted in the behavior of matter under gravity, radiation, and feedback, and they are the questions that the Webb observations are prompting us to address with renewed urgency and rigor. The light travels, as it has for billions of years, indifferent to the models we construct or the interpretations we apply. It arrives, it is detected, it is measured, and it becomes data. That data, in the hands of scientists equipped with the tools of analysis and the frameworks of theory, becomes knowledge. And that knowledge, when shared and scrutinized and tested against further observations, becomes understanding. This is the process that is unfolding now, driven by the remarkable capabilities of the James Webb Space Telescope and the equally remarkable efforts of the researchers who design the observations, collect the data, analyze the results, and build the models that seek to explain them. The early universe, as seen through Webb, is a realm of extremes and of rapid change, a time when the first structures were taking shape and the future character of the cosmos was being determined. The galaxies detected in that era, bright and complex and chemically enriched beyond initial expectations, are signposts of that transformation, markers of the processes that turned a nearly uniform sea of gas into the hierarchical, structured universe we inhabit. Understanding those processes, refining the models that describe them, and reconciling observations with predictions are the tasks that define this moment in the history of cosmology, tasks that are being pursued with energy and creativity by a global community of scientists. And so the light, detected and analyzed, continues to reveal its secrets, slowly and incrementally. As the tools improve, the datasets grow, and the models evolve. The universe, vast and ancient, holds many more secrets, many more surprises, many more revelations waiting to be uncovered. The James Webb Space Telescope, peering into the depths of space and time, is one of the instruments through which those revelations will come, and the light from the earliest galaxies, light that challenges and inspires, is among the most profound of those revelations.